Hi everyone and welcome to my talk. I am Umair from Lancaster University and I am going to present our paper exploring personalized vibrotactile and thermal patterns for affect regulation. The co-authors of this work are Corina, Niaz, Chalabianloo and Ersoy. I will start by highlighting the motivations behind this work, then I will cover the aim of the research, followed by introducing our method and findings. Finally, I will highlight key takeaways. The motivation of this work comes from personalized haptic patterns for affect regulation. Haptics can act as a distraction, cue specific thought patterns, or influence the experiential, behavioral, or physiological component of an emotional response, all of which are important parts of affect regulation process. While effective technologies for regulation rely on control of physiological responses, the mapping of such responses onto the interface element is usually provided by the researchers. We know little of how people may benefit from engagement in the design of haptic patterns for affect regulation. We report an exploratory study with 23 participants who were assigned to one of two groups. One group created either vibrotactile and thermal patterns for affect regulation and subsequently received these personalized patterns on the wrist through the use of haptic actuators during a stressor task. The other group did not create and receive any haptic patterns but went through the same stressor task. To understand the rationale behind personalized vibration and temperature patterns and their effectiveness, we conducted semi-structured interviews with those participants who received haptic patterns. We also collected self-reported measures of anxiety using SIGCHI questionnaires as well as heart rate variability data related to stress from all participants. For vibrotactile patterns, participants created high-frequency vibrations 65 beats per minute and low-frequency vibration 30 beats per minute. Majority of participants created low frequency vibration of 30 beats per minute and associated the vibrations with their heart rate. They created a low frequency vibration that would represent a slow target heart rate when they need to calm down. Participant 9, for example, mentions, I went to the lowest 30 beats per minute I could get. The reason is that I felt slower. It was necessary to calm down at a slow rate. Similarly, participant 13 created 65 beats per minute frequency associated with the vibrations to their heartbeat. She used the resting heart rate as a baseline and mentioned that feeling 65 beats per minute heartbeat rhythm on the wrist would help her bring the increased heart rate down during intense fear. Only two participants did not associate the vibrations to their heartbeat. Instead, they valued the slow rhythms created by the vibrations. Thermal actuator allowed people to create warm up to 16 degrees and cool up to minus 11 degrees. Half of the participants chose thermal patterns by increasing the temperature by 2, 5, 7 and 10 degrees. Interestingly, all participants choosing higher temperature referred to heat as warmth and did not go beyond 10 degrees, as it felt hot. They found the feeling of warmth as comforting. Participants 4 and 6 related the feeling of warmth to human touch, as if someone is holding my hand. The other group of participants chose to decrease the heat by minus 8, minus 10 and minus 11 degrees. They report that the feeling of cool on a particular place, such as wrist, is quite unique and unfamiliar, as they are more used to getting or feeling heat in everyday life, rather than cool. It is quite different. It's like putting ice cubes on your wrist, which kind of cools you down. Through experimentation, all these 4 participants discovered that cool feels more pleasant than the warm, so they all chose the values at minus 8 degrees or lower. This preference for cool was usually expressed in contrast to perceived negative experience of heat. In addition to interviews, to further explore the impact of haptics on subjective and objective measures of anxiety and stress, we also employed a between-subject design. For subjective measures of anxiety, we found that participants experience significantly lower anxiety measured by STI scores with either thermal or vibrotactile patterns compared to those who received no haptic patterns. For objective measure of stress, we found that the main effect of haptic patterns made by RMSSD was approaching significance. The mean values under temperature or vibration patterns were higher than the RMSSD under no haptic patterns, indicating again lower stress for those participants experiencing haptic patterns. Findings indicate that the participants perceive vibrotactile patterns through three experiential qualities: heartbeat, rhythmic flow, and slowness, which have been limitedly explored in the context of affective health technologies. They not only related vibration frequency to their heart rate, but to heart rate in a non-anxious state, using the low pace of the vibration in order to regulate their heart rate. They valued the rhythmic flow of these slow vibrations, which they could follow through entrainment, in order to slow themselves down during the stressor task. Another important aspect related to these qualities is the visceral experience of vibrotactile patterns, allowing participants to follow their rhythm as if it was their own heart. These findings support the view that with the right frequency, vibrations have the potential to be experiencing as coming from the body, more specifically when linked to the rhythm of cardiac system. For thermal patterns, participants perceive them through qualities such as subjectivity and focus, warm, touch and comfortable, cool, pleasant and noticeable, gradual changes of warm and cool through metaphors. Moving forward, I will highlight key takeaways based on our findings. We highlight the value of supporting implicit affect regulation through entrainment of slow bodily rhythms. We encourage designers of affect regulation technologies interested in entrainment to focus on slow rhythmic patterns, mapping heart beating rhythm, and future work to explore how to support effortless regulation of slow breathing. Rhythm can be created through other sensor modalities, such as visual or oral ones, through dynamic stimuli that can rhythmically change in time, or even through a different haptic submodality in the form of thermal patterns designed to rhythmically change in time. This is particularly interesting as it could allow integrating the benefit of rhythmic entrainment currently supported by vibrotactile patterns with the expressive and hedonic qualities of thermal patterns. While low-frequency vibrations offer effective haptic modality for affect regulation, thermal patterns were particularly valued for their expressiveness and hedonic qualities. We suggest that they can be leveraged as rhythmic patterns designed for entrainment to slow bodily rhythms. Supporting personalized and adaptive patterns. We want to emphasize the value of users personalizing their patterns for affect regulation. We also suggest integrating actuators with biosensors in order to provide real-time adaptive actuation that can be dynamic and vary with the changes in stress levels. Thank you. Please feel free to contact us if you have any questions.